For over a century, our understanding of the universe has been built on a model we could never actually see. In school, we are taught that atoms are like tiny solar systems with a dense nucleus orbited by distinct electrons. These ball and stick models are useful for chemistry, but they are abstractions. For a long time, there was a hard physical limit to our vision. No matter how powerful we made our glass lenses, the smallest building blocks of reality remained hidden behind a veil of light itself. To understand why we couldn't see atoms, we have to look at the nature of light. Visible light behaves like a wave, and waves have a physical size called a wavelength. If you try to look at an object smaller than the wavelength of the light you're using, the light simply bends around it, a phenomenon known as diffraction. It's like trying to feel the shape of a needle while wearing thick oven mitts. The resolution of our eyes and our best optical microscopes is fundamentally limited by the size of a photon. The breakthrough didn't come from better glass, but from a radical shift in physics. In the 1920s, Louis de Broglie proposed that particles, like electrons, could also behave like waves. Crucially, the wavelength of a fast-moving electron is thousands of times smaller than that of visible light. This meant that if we could somehow use electrons to illuminate a sample, we could bypass the diffraction limit. We wouldn't just see cells or bacteria, we could potentially see the atoms that make them up. In 1931, Ernst Ruska and Max Knoll built the first electron microscope. Since you cannot focus a beam of electrons with glass lenses, they used something else: magnetic fields. Electrons are negatively charged, so their path can be bent by magnets. By stacking electromagnetic coils in a tall metal column, they created a lens system for the invisible. This first device surpassed the resolution of light microscopes almost immediately, proving that the subatomic world was no longer just a theoretical concept, but a place we could visit. Inside a modern electron microscope, the environment must be perfect. The entire column is a vacuum, emptied of air so that electrons don't crash into gas molecules. At the top, a filament or a crystal is hit with a high voltage, firing a stream of electrons downward at nearly the speed of light. These electrons pass through the magnetic lenses, which squeeze and focus the beam into a point so sharp it is narrower than a single atom. It is a journey through a void to see the solid. There are two main ways we use these electrons. In a scanning electron microscope, or SEM, the beam bounces off the surface of a sample, like a flashlight scanning a dark room. This gives us those famous high-contrast 3D images of insects or pollen grains. But to see atoms, we often use transmission electron microscopy, or TEM. Here, the beam is fired through an incredibly thin slice of material. The atoms inside the sample scatter the electrons, creating a shadow-like projection on a sensor below. For decades, even the best electron microscopes produced slightly blurry images. This was due to spherical aberration. The magnetic lenses weren't perfectly shaped, causing the electron beam to smear. It was like looking through a pair of glasses with the wrong prescription. It wasn't until the late 1990s and early 2000s that aberration correctors were developed. These are complex sets of computer-controlled magnets that cancel out the distortions in real time, finally sharpening our view enough to resolve the individual columns of atoms in a crystal. When we finally look at an atom through a modern TEM, it doesn't look like a solid ball. Instead, we see a soft, glowing focal point. What we are actually looking at is the electrostatic potential of the nucleus and the dense cloud of electrons surrounding it. In materials like graphene, we can see the perfect hexagonal lattice of carbon atoms, looking like a honeycomb made of light. For the first time in history, the void of the atom has a shape we can record and measure. Seeing atoms is only half the story. We have also learned how to touch them. Using the fine tip of a scanning tunneling microscope, researchers can use electrical forces to pick up a single atom and place it somewhere else. In 1989, IBM famously spelled out their logo using 35 individual xenon atoms. Today, this precision allows us to build quantum dots and custom alloys, arranging atoms one by one to create materials with properties that don't exist in the natural world. As we push the limits of this technology, we are moving beyond still images to high-speed movies of the microworld. We can now watch as atoms shift during a chemical reaction or observe how heat vibrates a crystal lattice. We are no longer limited by the physics of light, but by our own ability to process the vast amounts of data these microscopes produce. We have moved from imagining the foundation of our world to witnessing it in motion, turning the invisible into the observable.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.